Today's video will define the robustness software design metric. Hello, I'm James Helfrich. One of the most important metrics we have in the quality of software is robustness. This tells us how much assurance we have that our software works as expected. This video will define that metric. So why does robustness matter? Well, the first example is on July 28th, 1962. The Mariner 1 space probe was destined to go to Venus, but it failed to launch. There was a period rather than a comma. The programmer typed do 15 I equals 1.10, and the correct line of code was I equals 1, comma 10. In the former case, it's 1.1. The second case, it counts from 1 to 10. This constitutes a single pixel on the display, but the code was not tested properly and the launch failed. Another example. In 2004, the United Kingdom's Child Support Agency developed a record-keeping system called the CS2. Within a week, over 1,000 problems emerged, with over 400 have no known workarounds. The cost of fixing the system, £768 million. On the 23rd of September, 1999, the Mars Climate Orbiter entered Mars's orbit in preparation to land. After 9 months and 669 million kilometers, it was intended to skim 57 kilometers above the surface of the planet. Instead, it plunged in too steeply and burned up. The problem: part of the guided system used English units and part used metric units. And as a result, it did the wrong math. On the 1st of August 2012, the Knight Capital Group activated the new trading software called SMARS for Smart Market Access Routing System. This system is capable of executing thousands of stock trades a second. Unfortunately, there was a testing system called PowerPeg, which bought high and sold low. Well, this is the opposite of what you really want to do to make money. Normally you want to buy low and sell high. This testing system was still in the system and, on the morning of 1st of August, was turned on by accident. In 30 minutes, SMARS lost the company $440 million. So what is the software quality metric of robustness? Well, one way to look at it is robustness is the degree of resistance a class has from being placed in invalid state or sending invalid data to the client. Or robustness is a measure of how well the class avoids introducing bugs into the code base. Or robustness is the degree of confidence one can have in a function, class, or component that will work as expected. Or robustness is the amount of rigor that has been applied to the testing process to ensure the code will work as expected. Or robust code can be relied upon to always produce valid output and exhibit predictable behavior. All these are valid definitions of robustness. So the question is, how do you determine how much confidence you can have in software? Well, we have 5 levels of robustness. The first is proven. The design was formally proven to be robust. We took the code, reduced it to a mathematical equation. We ran proofs on it to determine our level of confidence in it. Below that is resilient. And resilient can be achieved through thorough white box testing. You have a complete set of test cases, and each test case is implemented using unit tests, and this will thoroughly exercise the software. One level below that is strong. Strong is characterized by rigorous and systematic black box testing. One level below that is tested. We're going to use ad hoc black box testing. And finally, the lowest quality of all is fragile, only tested in very restricted circumstances. The higher the level of robustness, the more confidence we can have that a software will work as expected. So the question, how do you design for robustness? Well, it is far easier to design a class with robustness in mind than try to test in robustness. If a class will need to be strong, resilient, or proven, there are a few things that can be done to make this process much less painful. And let's see what those are. First is start the test plan early. During the design phase of the software, start asking yourself, how can you provide robustness assurances? How can you create unit tests that work as expected? Or how can you design the code that will facilitate mathematical proofs for proven? Second, produce well-defined output, but accept poorly formed input. So every time that we have a function or a class, we want to be as resistant as possible to malformed input, but in every situation, we must ensure that we're always in a valid state and we report valid input. Third, maintain a test plan as you go. Remember that the software creation process is not just about typing code, but it's about learning about the problem domain. And as we learn more, we can uncover more test cases, and these test cases will give us more assurance that our code is tested properly. Next, design white box tests as you implement the code. The best way to do this is use test-driven development. First, write the test, then make sure the test fails. then write the code, and then make sure the new code actually passes. We want to have 100% of all the code to be exercised in our unit tests. And finally, use formal representation whenever possible. When we design our code with robustness in mind, then we can make code with simpler input, and we can use functional programming techniques, which will facilitate using formal methods to verify our code works as expected. Now, keep in mind, most of the time, we don't need this degree of rigor to give the client the assurances their code will work as expected. But in situations where it's difficult or impossible to thoroughly test the code, or where the cost of failure is extremely high, I'm thinking medical or aerospace applications, then formal representations will definitely help and give us a higher degree of robustness. We can learn more about robustness in the Defining for Robustness section of the Robustness chapter of the Software Design textbook.